All right. So we will start the second lecture. Now, I promised last time the lecture will be about filters. Maybe I didn't mention also the lecture is going to be quite long, as in like in terms of materials. In terms of time, hopefully still the same, the allotted time that we have. But yeah, there is a lot of material. But hopefully it is also simple enough. All right. So I think the best way to introduce this lecture is, actually to start it. So I think we'll understand where we are quite fast. Oh, good. Everyone is in the class. Nice. Okay. Now we will begin by quickly remembering where we left last time. So remember we studied circuits, right? We reviewed a little bit of electrodynamics. We in particular circuits. So what we saw last time is, for example, RL circuit, right? Resistance, impedance, right? RL circuit. And here was an image of the simplest, you can say, case of series RL circuit. Here's the resistance. Here is the inductor. And we have voltages that can be measured across the resistor, right? So voltages that will be measured, let's say, placing electrodes on both sides of the resistor. By electrodes, I mean like connectors of your multimeter, let's say, right? And here you can measure a voltage across the coil, right? Across the inductor. And here you have input voltage, obviously. And that is pretty much all, all there is to it. It's a very simple circuit. Now we also saw that differential equation of the circuit looks like this. Why does it look like this? Because of Kirchhoff's law, second Kirchhoff's law, voltage Kirchhoff law. It says that the sum of all voltages across a closed circuit is zero. So we have one input voltage and two load voltages, you could say, this one and this one. And the sum has to be equal to zero. So putting input voltage on the right-hand side and loads on the left-hand side, we have Kirchhoff's law. So the sum of loads is equal to what power source gives us. And in particular, the only thing, like what we notice here is that this is obviously Ohm's law. The voltage across resistor equals to current times resistance. And here, this is a characteristic equation for inductor. So this is the fact that inductor, voltage across inductor is equals to inductance times the derivative of the current, right? That is how inductors behave, right? Okay, so this is how we get this equation. Now, that is our background. Now we can start thinking about it. So first of all, let us consider short circuit. So short circuit is when we ignore the input voltage, and instead we consider this circuit to be shorted like this, right? So we introduce additional wire that just shuts, like there is no input, it's just a closed circuit. Let's think about what's going to happen. So this means that the right-hand side of the equation, where input voltage used to be, is now equal to zero, right? It's now equal to zero. So this is a new equation. It is still a differential equation. Notice it is still a differential equation, but now without input. Just from the fact that it is a differential equation, you can already say something about it. First of all, it means that the solution to this equation is going to be a time function. differential equations, ordinary differential equations, the solutions are always functions of independent variable. In this case, independent variable is time, here, time. So the solution is going to be time function. So what you know is that a short circuit, even without power source, but with inductor, is going to have a solution that's going to change with time. So the current is not going to be static, it's going to change with time. In a way, you could say that that means that some kind of electricity, electrical energy was stored in the inductor. That is a crude way to put it, but you can say that something is, something is there because the current is not going to be zero, for example, or not going to be, there is not going to be anything static. Things are going to change. So you could say dissipation of energy is going to happen. All right. So that's already you can observe it simply from the fact that this differential equation. You don't need to solve it or anything like that. Now, let's attempt to solve it. The first attempt we can do is to bring this to the left-hand side. Standard thing for first order differential equation. We know that the solution is going to be exponential. If you remember how it's done, then clearly you can see that this is going to be coefficient of the exponential here, right? You have going to have initial conditions here, and that's it. That's a standard solution for a first order linear differential equation. So you can just remember it. If you don't remember how it's done, but you kind of remember general principles, you can think about it in terms of dividing everything by lambda, then integrating both parts. You would have a what do you call logarithm, natural logarithm on the left-hand side because it was 1 over I di times di, right? 1 over I becomes logarithm, then you exponentiate both sides, and that's how you get all this stuff. And this is how you get it. So all of this is nice, and this is the analytical solution. Just in case, I would sometimes drop some mathematical recommendations, so please be patient with me. In case this is not obvious for you, make sure you review your differential equations, at least the first order linear differential equations, because that's just the important piece of mathematics to understand, like how to solve this type of equations. But that's like very basic and it is very important. All right. So this is a solution. That's it. We can already know how it behaves. Here, we can make observations. So let's see if we have a slide. Yeah. So first of all, eigenvalue of this equation is, or of the system, or the way you want to say it, is minus r divided by L. Let's go back. So eigenvalue of a is going to appear here. This is eigenvalue for a scalar case. There is one value. There is no matrix, so maybe the word eigenvalue is not very good. You can say root of characteristic polynomial, root of the equation. There are plenty of ways to call this number. But yeah, this is eigenvalue. So this would often, from many perspectives, you can say that this determines how the system is going to behave. In particular, since this number dictates how the exponential is going to behave, right? So this is exponential, this to the power of minus r over L times t, right? So if this overall number, okay, if this number is positive, the exponential is going to grow this time, right? If this time this number is negative, it's going to diminish this time. Okay. Now, for us, this number is always negative. Why? Well, because R is positive and L is positive. Resistance cannot be negative. inductance cannot be negative. They're physical parameters, so we know their values. That is one part, like before, everything I was saying before was, you could say, part of materials on a course of differential equations or control theory. Both courses deal with exact same equations. But now comes mechatronics. Those parameters have physical value. So you don't have to say, oh, there are 4 different cases when L is bigger than 0, when L is smaller than 0, etc. No, there is no 4 case. There is one case. L bigger than 0, R bigger than 0. No other cases exist here because those are physical parameters. So we take advantage of that. We can instantly say how this equation is going to behave. So this is negative. And the system is what we call asymptotically stable. If you remember your control theory course, you know what it means. It means that the solution is going to decay towards 0 exponentially. Right? In this case, exponentially, but anyway, going to decay towards 0, not towards any other number. It's going to asymptotically approach 0. In our case, it's also going to decay exponentially. So it's even stronger conditions than asymptotic stability. Good. So what we have is stability of the system. We know that this short circuit is going to be stable, so the current is going to go to 0. That is not surprising. Any physical system which has energy dissipates energy. So you would expect a solution which would dissipate energy. If you had some energy that could be dissipated, it would be dissipated. That is common sense for autonomous systems. So for systems which are isolated from power sources, from external power sources, like a pendulum is going to stop eventually, right? Anything like this which has mechanical energy will lose it, cease moving. Same with electrical systems. So this is not a surprising fact. You would expect it from physical standpoint. All right. Now, this was, what we say. So the current exponential decays from initial value to 0. Notice it's not going to oscillate. Oscillatory behavior is typical for linear systems, but second order and bigger. This is a first order system. So this solution, there is no oscillations possible here. In fact, you could say that since this eigenvalue is real, it is a real negative eigenvalue, there is no oscillations. If it was imaginary, there would have been oscillations, but imaginary eigenvalues are impossible for the first order systems anyway. So we don't expect oscillatory behavior in this filter. That is, one other thing that you can notice immediately from solution. Now, what we also can notice is that the bigger the inductance, right, inductance here, the slower is exponential decay. Why? Well, let's look back again at this equation. Here we have this number. If it is a large negative number, then the decay is going to be fast, right? The exponential is going to go to 0 faster. If there's a small negative number, the decay is going to be slower. So what makes it be a large number? If the denominator is, I'm sorry, sometimes mix them up. If something, if L is bigger, the ratio is going to be overall smaller. If L is smaller, the ratio is bigger, right? I believe we call it denominator, right? Then for the R, it is vice versa. We have the bigger the R, the bigger the overall number is. The smaller the R, the smaller the overall number is. So that's how we can tell how they are related to exponential decay. Now, what we have is that the larger the inductance, the slower is the exponential decay. The larger the resistance, the faster the decay. This again physically makes total sense. Inductance, in a sense, is something that prevents the current from changing. So the larger the inductance, the less change we expect. But it has to change to 0, right, eventually. So the larger the inductance, the slower it will change to 0. R on the other hand, is what dissipates the energy, right? You remember last lecture we said that the power of heating is exactly the same as the power of a resistor. In a sense, it is a resistor that's going to dissipate the energy here in the system. So it's intuitively it makes sense. The bigger the resistor you have, the faster you're going to dissipate your whole energy, right? Okay, so this was the analysis of the short circuit of this equation. So far, very basic, but you see the tools, right? We just simply use mathematics. There is no, physics or anything beyond. The only physics that we used so far was just knowing how to construct this equation, like Ohm's law, the characteristic equation of the this coil here, right? That's it. Kirchhoff's law, everything, but outside of that, it was pure mathematics. All right, that's important to remember because this mode of analysis is important for us. We have to be masters of this kind of analysis, and we have the tools, mathematical tools. Right? So it's important to keep it in mind. Stop me if you have questions. I'm going to go fast this lecture just to avoid breaking it into two because we have quite a bit of material. But please stop me as soon as you think something is not clear. You can also write in the chat. I'll keep looking. Okay. Now let's consider now the solution with the input. So with arbitrary input, so just some function v of t, we can find analytical solution. Analytical solution is going to have this part, which is what we saw before. This is just a solution to the homogeneous part of the equation, how we call it. This is the homogeneous part of the equation. Right? Homogeneous means that it is various derivatives of the variable I in this case. So homogeneous part of the equation. And that's the solution. You can say this has to do with initial conditions. Here is the initial conditions. Okay. And we have this, which is we have this, which is the sometimes we call it particular solution. This has to the word particular solution is maybe like not as descriptive as one would want it, but it's a good word. It's just not very clear what it means here. Basically, it's important to remember that this particular solution has to do with a particular, you could say, input, right? And the input is any function of time. Right? In any case, this is the analytical solution that relates to this input. Okay, it is independent of initial conditions. That is a very nice feature of linear equations that they have this independence. So initial conditions act their way, external function acts in their way. Now, instantly you can notice that we cannot now say anything about the function being, converging to zero or converging to something else. Nothing at all. Why? Because we don't know what v of t is. V of t enters here under the integral. And after some manipulations, you'll be able to integrate it, depending on what this function looks like. And yeah, we'll get a solution. But it's not very obvious what we are going to get because we don't know what v of t is. But at least we have this very nice general expression. So while it is not mysterious, we cannot say readily what's going to look like. And let me stress one last time. It doesn't make any sense to ask about stability of the system or convergence or anything like that because it's too general. We don't know what v of t is, so we cannot answer those questions. Right? And we shouldn't ask them in the first place for the step system. Okay. Well, this is a general solution. As you can see, previously we were able to say anything. Right now we almost said nothing. So let me consider bring you now to the middle road, which I think is maybe the most important part of this whole discussion. And that is, no, before we go to the middle road, I guess we'll get there step by step. First step towards this middle road is to consider constant input. So V is equal to constant, to some constant. So the voltage is equal to something, just some number, right? And we can consider steady state of the circuit, steady state. So after the transient process is over, we will have some steady state. What does it mean to have a steady state? Well, let us go back to the equation. Steady state means that there is no change. So since there is no change, this guy will be equal to 0. This guy is going to be equal to 0. But if we had 0 on the right-hand side, that, as here in the short circuit, that would also mean that I is 0. So the only steady state that a short circuit can have is trivial solution, no current at all, which makes sense, right? Short circuit, what kind of current can you have there? No current at all, like in steady state. But in the differential equation here, if we get rid of, let me try to get rid of it. If we get rid of this guy, what we have is still some equation. It's no longer differential, but it is still an equation. So we have I, we have V, right? That is that's what means to be a steady state solution. We assume that the variable doesn't change its name, its value. So derivative of I is equal to 0. I is equal to constant, to some constant. That is very easy to do for differential equations because it just means we set to 0 everything that is a derivative, and we get this part remaining. Now let's look at the slide where we left. All right, yeah, exactly what we saw previously. This is the equation. What it becomes. So impedance doesn't do anything. The voltage across impedance is equal to 0, and we have only the equality between the voltage across the resistor and the voltage of the input source. And the state solution looks exactly like Ohm's law. It says that the current in the circuit will be equal to the input divided by the resistance. This makes perfect sense physically too, right? We said that impedance only acts on change of the current. Since there is no change in steady state, it doesn't act. So it is as if there is no impedance at all. Makes sense. All right, this is one special case when everything is very clear. It's not short circuit, but it is almost as simple as short circuit. Okay, and that's because because we consider steady state, not the whole solution, but only the final result. Okay, now where I wanted to bring you. This is quite general, but it is still solvable. So that's why we maybe one of the reasons why we like to analyze it, but also it is very useful. Consider this case. You have input voltage, and it is equal to a harmonic function. So it is some constant C times cosine omega t, so some harmonic function with the frequency omega, plus d times sine omega t. Right? If you remember a little bit your trigonometry, or if you had some maybe a course on Fourier transformation or anything like that, maybe you recognize that this expression here could be transformed using one of the most important trig identities into an equation something like a times sine omega t plus phi, right? So we could transform this expression into a single harmonic function, but with the phase with the phase. Like here we have zero phase, you see, omega t. There is no plus phi, but we could add the phase and then we could get rid of one of those two harmonic functions. But we don't have to. This is perfectly reasonable for us. All right. So this is what we have. This is what we have. Now, let us find a here I'm abusing my own notation already. Probably is a little bit unfortunate, but hope you forgive me. We'll find, I say, steady state response. I should say maybe harmonic steady state response or something like this. Yeah, of the system to this input, because of course it's not steady. It's not a steady state response in the sense of being constant. It is a steady state in the sense of initial conditions being played out. I guess just to avoid confusion further on, let me spend 1 minute explaining what I mean. Let me go back to the equation here, to the solution, sorry, here. Notice that this equation like has this solution, right? And we said that this solution has two parts. This part related to initial conditions, we can call it homogeneous solution. This particular solution has to do with the right-hand side. Okay. All right. This homogeneous solution will eventually, after a long time passes, will play no role whatsoever for a stable system, because for a stable system, the eigenvalues here are negative. So we have something that dwindles into insignificance. And after a sufficient time passes, we would be able to completely ignore this part and only consider the particular solution. So solution would, roughly speaking, look like this. Okay, after sufficient time passes. And this is a very important way to analyze a system, because for systems with sufficiently large negative eigenvalues, the time doesn't have to be like centuries. It can be seconds, sometimes milliseconds. So the transient processes are very fast. And also, they're not very important, right? Also, initial conditions don't have to be crazy. They can be perfectly sound. But on the other hand, analysis of what's going on here in the particular solution is extremely important, as I'm going to show you in a minute. So for us, it is important to analyze particular solution, right? Sometimes. And I guess this is what I'm basically talking about, particular solution. If the input wasn't, like if the input was constant, we could talk about steady state response, right? But since input is not constant, input is harmonic, the particular solution is also going to be harmonic. For me, it somehow makes sense to call it steady state in the sense that it is repeating itself. Like the transience where we have something that constantly changing is over. We just have a repeating pattern, which is perfectly described by phase and amplitude. But I understand that steady state also sounds like a constant. Constant, steady state sounds like synonymous words. So maybe it's unfortunate choice of words. I'm not sure. But hopefully I explained the essence of the issue, right? But particular solution is going to dominate the behavior of the system after the transient process is over. So when sufficient time passes and initial conditions no longer influence what we see as a behavior of the system, like they are dwindled into nothing because of the negative eigenvalues here. All right. So what we're going to find is let's say particular solution to this equation. I will try to stick to that word. we're going to try to find a particular solution of the to the system in this form. Okay. What is up? What am I doing? What am I doing? Let me bring it to your attention. So input looks like a harmonic function. Harmonic function is characterized by frequency, amplitude, and phase. Amplitude and phase are both encoded in those two variables here, C and D. Again, this comes from a trig equality, trig identity, which says that you can transform this type of trig function into a single like sine with a single amplitude and a single phase variable, right? So this is this C and D encode both phase and amplitude of this harmonic function. It is a single harmonic function, like it's not a, it cannot encode like sum of harmonic functions, but as one it encodes one harmonic function perfectly. Now for a first order ODE, the solution of a first order ODE when the input is a harmonic function is also a harmonic function. So that's something you just can know. For a first order linear ODE, solution for a particular solution is going to be a harmonic function if the input is a harmonic function. Now, and the frequency is going to be the same. That is very common stuff. Frequency is going to be the same too. So here I encode again the phase and phase and amplitude by those two constants, A and B. So we have a series of 4 constants, okay? 2 constants that determine the amplitude and phase of the input signal, and 2 constants that interpret amplitude and phase of the output signal. That's what we have. Now, what we want to find is the relation between the output, I mean like the solution current, right? This. So we want to find the relation between the parameters of the current, so amplitude and phase, and the parameters of the input, right? That's what we want to find. Okay, let's do it. Let's do it. So first, the way we do it is by differentiating this equation. Like this equation, we can differentiate it, and we get this. I just point out that we have omega here because when you differentiate sine omega t, for example, you get cosine omega t plus times omega, right? So omega gets out of the brackets. It's a chain. It is a chain rule, right? Chain rule. Okay. And you remember that derivative of cosine is minus sine. Derivative of sine is cosine. That's why we have minus here and plus here. Good. Now what we are going to do is we are going to substitute equation 10. So this equation is going to be substituted into the original differential equation. This is going to also be substituted into the original differential equation. And this is going to be substituted into the original differential equation. So it will be L times this plus R times this equal to this. That's what we're going to do. Right, let's do it. Let's see. So here is the result of substitution. Large salad of trigonometric functions. And we can rewrite it by collecting terms in front of sines and cosines. And it stops looking intimidating. We have L omega b plus R a minus c times cosine minus L omega a plus b rb minus d times sine equal to 0. So it's quite easy. Quite easy. I just collect constants in front of trigonometric functions. this would always hold if this is equal to 0 and this is equal to 0. If both of them equal to 0, then of course the result will be equal to 0. Okay. If they're not equal to 0, then good luck. Good luck making it equal to 0. Like, making it into our identity. So this is why we can write those two equations. We just say that coefficients in front of cosines and sines have to be equal to 0. Right? We're still trying to just find the relations between A, B. So the coefficients that describe behavior of the current, and coefficient CD, what describes behavior of the input voltage. Okay, let's solve this equation. So this expression I rewritten it so that C and D are on the right hand side and A and B are on the left hand side. I can write it in a matrix form. So here's a matrix. Here are our, A, B, right? You can check that this is the same thing, right? Like R times A, right? B times L omega, etc. So the same thing. I rewritten it as a linear equation in a matrix form. Now I can solve it. I didn't have to do it in a matrix fashion, but first there is a huge benefit in terms of computations. And second, this exercise is just like something that I recommend. Every couple months, try to invert a 2x2 matrix. That would help you as an engineer. You will not forget how to invert matrices, first of all. And second, eventually you will get familiarity with those procedures, and it will just become like you'll get better. Is what I'm trying to say. Even though it is extremely primitive, like there is almost nothing here that looks like it is going to be challenging. It's a good exercise. Okay. So we invert this matrix, and the inverse of this matrix is quite simple. If you remember how it's done, you remember that you would have to find determinant, determinant, inverse of the determinant. That's why it is in the denominator, right? Inverse of the determinant. Now, what you have here is those would be changing places, but they are the same, so they stay. And here you would have change of signs. That's why the sign kind of migrated from here to here. Anyway, the formula for analytical inverse of 2x2 matrix is available everywhere. So make sure you look it up. Maybe I'll attach a page to the end of the lecture just for a reference. But yeah, it's quite easy. Okay. So this is the analytical inverse of a matrix. So we can now find expression for A and B. How do we find it? We find it by multiplying this inverse of a matrix times C and D. What I do next is I just compute this part times this, and I don't do anything with this coefficient. You will see now why it was beneficial to use a matrix formula. Well, what we are going to do next, yeah, by the way, here you can just check that I multiplied those matrix and vector correctly. But, hopefully, is correct. Should be. Now, what we can do is now ask important questions. Here is the important question that we really want to ask. How the amplitude of the current, which is, this is how it is calculated. A squared plus b squared makes sense somehow, right? Yeah, this is the amplitude of the current. Again, this comes from the trigonometric identity, which I should probably attach it to the end of the lecture notes. So this magnitude of the current depends on the magnitude of the input sine wave, which is this. So how are those two related? You have magnitude of the current, you have magnitude of the sine wave that is input. How are they related? Well, let us compute it. It sounds like a pain, but it is not a pain. So let me show you. To compute it, we need to find a squared plus b squared and square root. Well, first of all, when this guy can get out of the brackets here, because it's going to be, it is present in both a and b. When you square it, you just get a square, right, around the denominator. And then when you take square root, the square is going to disappear. And this expression is strictly positive. So because you can see it is a square root plus, square plus square times square, strictly positive. So nothing changes after you take square and square root. So this expression stays positive. So we can take it out of the brackets, is what I'm trying to say. And here it is, taken out of the brackets. Okay. And now what we need to do is let me do it this way. Take a squared, which is this squared, which is here, and b squared, right, which is this squared, which is here. I open the brackets, and what I will see is that in front of c, we have r squared and lambda squared omega squared. In front of d, we have lambda squared, omega squared, and r squared. So we can, take things out of the bracket twice. And what we'll get is this expression here. So you can choose like to, you take, c squared out of the brackets, and you take d out of the brackets. You realize you'd have same expression in front of both of them. So you take this expression out of the brackets, and that's what you have. All right. So this is what we get. This is what we get. Another way to achieve the same result is to realize that if we sum those two, we'll have 2l squared omega squared d squared, which looks like a expansion of a binomial, right? So anyway, this is what we have. Okay. Now, what is interesting here is that this expression and this expression are the same, but one is under square root and another one isn't. So when you cancel, you get this. Okay, this is the process. Mathematics is not difficult here. Well, notice now we have amplitude of the current is related to the amplitude of the voltage as, amplitude of the voltage times this factor, times this factor. So if you want to find amplitude of the current, you multiply amplitude of the voltage by this factor, 1 over square root of r squared, lambda squared, omega squared, okay, plus. Sounds very interesting, so you see, we found analytically the relation between those two. For those of you who understand where it goes, I want to stress that we did all of this using differential equations. We did not use Laplace, we did not use Bode, nothing like this. It just used analytical expressions here. That is the key point that I want to make. Okay. Right. Now, that's what we found is called amplitude gain. So this thing here is how amplitude of the voltage is increased or decreased by passing through the filter and getting current outside. Okay. So the amplitude of the current is amplitude gain times amplitude of the input. And this is called frequency response. Why? Because this guy here is the square root square of the frequency. So we can see how the gain changes with different frequencies. And we can plot this gain as a function of frequency. We can analyze all how it works, right? Let us do it first. But before we do, let us quickly see how voltages appear here. So we know that voltage across a resistor is just current times R. That means the amplitude gain of a voltage across a resistor relative to the input is the same as for current times, but just times R, right? So the signal is just, R times bigger. So there is no magic here. It's very simple like that. Now, the amplitude across the inducer, right, is lambda times the derivative of the current. Okay. So its amplitude will be given like this, right? Like this. Why does it look like this? Well, the reason is what you have to do is you have to look at this function, right? We computed before. So let me show. We computed here, equation 10, right? And you should look at this amplitude of this function. The amplitude of this function is the same as the amplitude of this function, except it is multiplied by omega. Why? Well, because a squared plus b squared square root is the same in both cases, but here you have also omega factor of omega. Like this minus sign here doesn't really change anything. The fact that sine became cosine, etc., again doesn't change anything. So the difference between those two functions is the factor of omega. And then here now we also have additional factor of L. That's why we have omega L. That's it. And you can see this is going to be the amplitude gain for inducer. So we found all those. Okay, now let us see if we can analyze. We analyze the current gain. Just for simplicity, I'm analyzing the current gain. So as frequency, and this is a frequency, remember, okay? As frequency goes to infinity, the gain, so let me, frequency goes to infinity, the gain, and this is the gain, goes to 0. Because the numerator is going to infinity, right? 1 over infinity is 0, right? Now, as frequency tends to 0, the gain goes to 1 over R. Because if lambda or L squared times 0 is 0, so we just have 1 over square root of R squared, so 1 over R. Okay. So notice this is, we just analyze equations, but now we back to physics. Back to physics. What does it mean? If we pass through this filter a signal with a very high frequency, like we go kilohertz, megahertz, gigahertz, right? Like very high frequencies. What's going to happen is nothing will pass. The filter will act as if, as if it is cut off. So we can expect that you'll see no current at all if you're trying to pass a high frequency signal through it. On the other hand, if you're trying to pass a very low frequency signal, you would see that eventually inducer will stop acting at all and will just behave like a resistor. Okay, the whole circuit will start behaving as a resistor, which is exactly what we saw when we studied steady state response here. Steady state response, when V is constant, is just the ultimate form of low frequency input signal, right? It is zero frequency. So everything makes sense, but now we analyze it in terms of frequencies, okay? But we, this corresponds to what we saw before, and this corresponds to how we understand inducers to work, right? They prevent fast changes. In a sense, what you can think of here is inducer kind of acts as a pseudo mass. If you imagine mass is what prevents velocity from changing, right? Very fast. Like the bigger the mass, the less velocity will change under the action of an input force. Okay. Now you can kind of imagine that if you have a very big object, right, and you try to move it very slowly in one direction and another direction, there is maybe a chance that it will move a little bit. But if you're trying to vibrate it, like just shake it back and forth, a very big object is just not going to move at all, right? Even if it is standing on ice where you don't have any dry friction, you cannot expect to shake a very big object, but you can expect to push it. If you're pushing it very, very slowly in one direction and another direction, then you could. But if you're going to try to vibrate it, nothing is going to happen. Even if the force is acting is the same in both senses. Like somehow it almost makes sense because you can say, oh, when I push it slowly, my force acts for a very long time in one direction and for a very long time in another direction, right? Whereas in a high frequency, you can say, oh, I'm only giving it like a half a second push in one direction, half a second in another. Of course, it's not going to go anywhere. Somehow physically intuitive, right? So in many ways, the inducer makes this filter act like a like this physical system that we just described, like a system with mass. Any questions about this so far? Okay. Before I continue, let me just make one remark. We are discussing current, right? We're discussing current. So I was telling that the current, amplitude of the current is going to behave this way, right? High frequencies is going to, amplitude gain is going to be tend to 0. Low frequencies is going to tend to 1 over R, okay? And if you measure your voltage across a resistor here, you're going to see exactly the same picture by times R. So high frequencies, everything tends to 0. Low frequencies, everything tends to 1, right? 1 over R times R is 1. That is quite interesting, right? You would see a gain on low frequencies of 1, amplitude gain of 1. Somehow again makes sense, right? The entire voltage that passes in is going to be dissipated on the resistor. So this is why the gain is 1. And sometimes electricians, people who work with electrodynamics, I apologize if I use incorrect terminology, like to talk about those filters as voltage dividers. Since voltage that is spent here is influences the voltage that is spent here, right? So you can say if input voltage is equal to the sum of those two voltages, what you can measure across a resistor, what you can measure across a inductor. So if your gain tends to 1 across a resistor, it means it tends to 0 across a inducer. On the other hand, if your gain across a resistor tends to 0, it means it will tend to 1 across the inducer, right? So in a sense, as long as you measure across a resistor, everything that we said is exactly exactly the same, current or voltage, right? But if you start measuring across the inducer, it's going to be completely reversed, because then on the lower frequencies, where the voltage here, the amplitude gain for the voltage across resistor, it is 1, then here you would measure 0. On the low frequencies, inducer acts like there's nothing, right? Doesn't no voltage is lost across the resistor, across the inducer. On the other hand, on the high frequencies, it is going to act like everything is lost here. Like this resistor is going to experience nothing, but the entire voltage is going to be measured here. So the gain is here is going to be 1, here is going to be 0. So they somehow antagonistic in this sense. And you can use the same circuit to achieve both behaviors. It depends on where you measure. So that's what we call voltage divider, because the sum of those two voltages is always equal to the input. Okay, that's just one comment that I wanted to make. It's quite simple notion, but you have to hear it. Okay, now what we have here is what we call low pass filter. Again, we are talking about current. Okay, high frequency signals are attenuated, so suppressed by this circuit, whereas low frequencies are not, like they are suppressed by in the best case scenario 1 over R or more. But if you measuring across the resistor, voltage across the resistor, not current, voltage across the resistor, then the name makes even more sense, because the lowest frequencies are not changed at all, but the higher frequency you use, the more it is attenuated. Okay, but the lower you frequency you use, the less it is attenuated. So that's quite interesting. Okay, okay, and you never see gain more than 1. 1 is the biggest gain you can have for measuring voltage across the resistor. Okay, that is it for this mode of analysis. So again, if you have any questions, ask. Interrupt me in the time, ask. Okay, moving forward. Now, this, as you could see, mathematically was a lot of work. So let us introduce a labor-saving device, which you already should have seen on 2 different courses. So I'm going to be very, very rapid. Very rapid. This is the Laplace transform. Laplace transform, mathematical object. You apply it to a time domain function, f of t. And what it looks like is this: a function f of t times Laplace kernel e to the power minus st, where this s is a Laplace variable. It is a complex variable. Okay, so it has a complex part and a real part. All of this is integrated from 0 to infinity along t. So this function is function of t. This is the same t. Okay. And as a result, you get a new function, which is a function of Laplace variable, f of s. This is called the Laplace image of this function. All right. In particular, Laplace transform of a derivative dt dx dt is equal to Laplace transform of the original function x of t, becomes something, times s. Well, this is a quite useful in control theory. We use it all the time, but here we are going to use it a few times too. So Laplace transform of a derivative becomes just transform of a function times s. Okay. if any of this is new for you, you should definitely review either control theory course or Laplace transformation course or ordinary differential equation course, like one of those. Laplace transform is, you will find it described in one of those courses. So make sure you review it. Here we can assume that this is already your background. Okay, now time domain ordinary differential equation for RL circuit, as we said before, looks like this. Now we can Laplace transform it. How is it going to look like? Laplace transform of L times di dt is L times S, because of the derivative, I of S. Okay, so L does not change, of course. Right? Constants, Laplace transform of constant is a constant. There is, doesn't change. Laplace transform of I, let me use different color. Laplace transform of I just write it as, Laplace transform of I. I don't know what I is. I just rewrite it in a different domain. And this dt, this becomes our S here. Okay. Here, Laplace transform of this becomes I of IR becomes IR, just a new domain. So R is not changed. I is as before becomes I of S. And lastly here we have V of t becomes V of S. So again, just Laplace transform. So you can see I didn't do anything. I just replaced the functions with their images in Laplace domain, but since I don't know those functions, I just write them with a new variable. The only thing that I did change is the derivative becomes S. Okay, that's it. Okay. So this is the same equation, but in Laplace domain. Now, what we can do is, looking at this equation, we could write it what we call a transfer function. What is a transfer function? Well, it is such function where we could say I is going to be equal to transfer function times V. How do we do it? Well, we do it by collecting I on the left-hand side and everything else on the right-hand side. We see that in this equation here, you can rewrite it as LC plus R times I equal to V. And we divide by LC plus R, and that's what we get. Right? We express I out. Right? So from this equation again, I express I, and what I would get is V divided by LC plus R, LS plus R, and then V. So the transfer function itself is this part, right? V is not part of transfer function. Okay, so this is a transfer function. It is a transfer function from V to I. Now, we could also find transfer function from V to VR. VR is voltage across a resistor. Remember, it is equal to I times R. So, but I is equal to this guy times V. So voltage across resistor is just same but multiplied by R. So the transfer function will just get R. Yeah. Right. So this R will just get here, right? See, because of this relation. Okay, so that was trivial. Voltage across the inductor, it looks like this. Where did we get this from? Well, remember, what is voltage across the inductor? Inducer. It is L times di dt. But what is di dt? It is S times I. S times I. So we have L times S times I. Again, we know what I is, so we just get this L times S in the denominator. Sure. Because we know what I is. We know the transfer function for I. So you can see how easy it is to work with transfer functions here. So far, we didn't achieve anything new. We just wrote transfer functions for everything. But that was almost trivial, right? Like I was explaining things which I could have skipped. Like I could just say, express to me, I as a function of v, you would have done it. Like it's very easy. Okay, now that we did it, we can use something that I'm not going to prove mathematically or anything. Just assume that you already saw it. And, there are plenty of videos and books that can explain it in details. That is how to find the frequency response of a function if you know its transfer function. Okay, of a differential equation if you know its transfer function. The way you do it is if you know transfer function v of s, you substitute omega I, omega j instead of s, and you compute the absolute value of the transfer function. Okay? You compute the absolute value of the transfer function. Absolute value. Okay. That's how you find frequency response. You get transfer function, replace Laplace variable with omega j, and you find the absolute value. Like simple explanation, and this is just like poetic stuff, not mathematics, but simple explanation looks like this. Your Laplace variable, you can think of it as representing a solution, like eigenvalue or a solution, you can say, to a ordinary differential equation, or second order ordinary differential equation. Kind of what it is. And yeah, kind of what it is. And as long as you're interested in frequencies, what you need to care about is the imaginary part. So you can set your real part to 0 and just look at the imaginary part. And that's kind of like what we're doing. There is a different way to look at it. That is like after the end of the transient process, the parts which have real parts of this, of those Laplace variables are going to decay to 0, and so on. But anyway, I think intuitively for us it is kind of clear that it is a complex part of the eigenvalues that matters for frequencies, and that's kind of easy to memorize. But if you want to understand it, you have to look at the derivation. That's quite interesting. So make sure you check it out. Anyway, so we have this nice way. Just substitute omega j into a transfer function and find its absolute value. How do we do this? Well, let's look at our transfer function. Our transfer function looks like this. Let's substitute into it omega j. So you can see here omega j is substituted into our transfer function. Oopsies, just 1 second. I will just make sure I color coded consistently. So we substitute it into the transfer function. That's what we have, right? That's the first step. Here, the one thing you can, try to keep in mind as a way to solve this equation, that is, you need to make sure that your denominator will not have complex variables. How to do it? Well, you multiply both numerator and denominator by conjugate of whatever you have here. So conjugate is the same thing, but with a different sign in front of the complex variable, you can see. Right? Like I'm looking at it and I'm having like a misgivings about where the sign is. Like I kind of would have wanted to be here, not like here. The change of sign. I'll double check after the lecture. Yep. So Yeah, but I don't think it is going to change anything. Yeah, I don't think it's going to change anything. So you multiply by this guy, for example, like what I did here. And what's going to happen is the expression down below. Yeah, the expression down below would give you. Okay, I'll double check after that. Anyway, I'm not going to. I think there is a minus sign lost here in front of this. They should be minus sign because the expression down below would be minus L2 omega 2, y minus because j squared is minus 1. Complex, that's what complex numbers do. And here would have like r times, minus r, you would get minus r squared. So I think there should be minus sign here. But it again doesn't change anything because we're going to take absolute value next time. Okay, so you multiply by this, you get this expression here. And that is how we get on top of this transfer function, the same as what we had on the bottom, but different sign. All right, good. So this is what we get. It's quite standard step. Next, what we do is we compute absolute value. Okay, remember, we need absolute value. What do we mean by absolute value? Well, it is this squared, right? This squared plus this squared. Okay. So it is real part squared plus imaginary part squared. Okay. So we since they share denominator we will we'll square it, then we'll take it out of the brackets and we'll take a square root, so nothing will change with it. So we can basically just push denominator through this without any change. It is just like a common factor. It doesn't like it goes unchanged. What will change are those values. You can see it is squared here. You can see this is squared here. Okay. Now notice that what we got in the denominator and numerator is the same function, but upstairs it is square root, downstairs it is nothing, so we get 1 over square root. Okay, so that's what we get. Suspiciously familiar. Suspiciously familiar. In fact, let us look at it. 1 over L squared omega squared plus R squared. Let us look what we got last time. R squared, L squared, omega squared. Same exact thing. So what we got here is, again, is a frequency response. So this is a gain. That is how the amplitude of the signal is going to change, depending on frequency. And you can see we got exact same solution as before. Now, before I'm going to go to like the rest of this, the rest of the material, let me note what I want to, like why we did all this. First, as you can see, this was easy. This is like Laplace, everything that we did with Laplace was very simple. Laplace transform itself is just a matter of replacing variables, like replacing derivatives with s, expressing something out, just trivial, like very easy. You can do it, it is just not a problem at all. Of course, we are lucky because we deal with very small transfer functions. For bigger transfer functions, it can be more difficult. But in mechatronics, we are not going to deal with bigger transfer functions. We have equations of the order 1, 2, 3. Fourth order is so rare, it almost doesn't exist. So we have quite simple equations, and that is why our Laplace transforms are going to be very simple too. That is number one. Number two, here we did use like a couple tricks, but this mathematics is not intimidating. I mean, you cannot tell me that this is complicated mathematics, right? So what I'm trying to say that analyzing it by hand is not only an option, it is easy, and you should do it. You should do it. Of course, there are automatic Bode plotters, and you can use them too, but there is no reason why you shouldn't do it by hand. Okay. Third, that is maybe the key. You can see that we got the same result by analyzing particular solution of a differential equation and by doing this Bode plot. I understand that the Laplace theory for you, for like engineer with computer science degree, sounds like alien mathematics. You had like a semester course on differential equations. You didn't have a dedicated course on Laplace transforms. You didn't have a dedicated course on other types of transforms, on like operators and so on and so forth. So the mathematics is obscure. Like, why does it have to be that frequency response looks exactly like what we have here, and so on and so forth? Like, all of this sounds very strange. And the Laplace transform is very involuted in this way. But if you don't trust it, you can always use mathematics, which is simple, finding solutions, particular solutions to the equation. And I showed to you how easy it is. You just propose a solution, which is also a harmonic function, and you do the linear algebra. That's it. It's easy. It takes space, like it takes time to type it, etc. But it is easy. So you could always check. You don't have to rely on magic of Laplace transform, what I'm trying to say. You can always check with your knowledge of simple differential equations. But you don't have to rely on cumbersome solutions you get from analyzing differential equations. You can use the elegance of Laplace transform. So you have both of those, right? You don't have to trust in any of the, like in one instrument. You don't have to rely on cumbersomeness of the second. You can use both when appropriate. And that I think is very important, because if you are going to give up on analyzing frequencies because you don't feel comfortable with Laplace, what are you going to use instead? Right? I haven't seen anyone who analyzes it with particular solutions, for example. Not that I ask everyone, but that's not what I typically find. On the other hand, if you're going to give up on analyzing frequencies because it just takes too much work to work with ODEs, which that I find a lot. People often give up on doing something because they think, well, this is like too much work. Maybe we can skip this step. Then I don't know. You can trust in your Bode plotters or something. If you're going to do it, eventually you'll probably start feeling like, oh, I don't like this instruments that I cannot verify. One way or another, it's not a good situation. You should be comfortable doing frequency analysis. That is the key. It is what engineers do, especially for small systems. And mechatronic systems are small systems, right? We are talking about a motor, single motor. We're talking about maybe a motor with a payload, stuff like this. It's very, very simple systems. And for those simple systems, you have to do exhaustive. You have to be exhaustive in terms of analysis. You cannot say, oh, it is stable in terms of Lyapunov, but frequency response, I didn't really look into it. Like, you cannot do this. This is nonsense in terms of engineering, because you have all your opportunities to study the system and to understand how it responds. So saying that I didn't do it because a little bit of work, that is not acceptable for mechatronic systems. I understand that this is acceptable for theoretical large-scale projects when you hope to at least achieve Lyapunov stability, and frequency response is not something that you can do, and so on and so forth. Even though this is only when you do it in the lab. Like, when you go to real life, you still have to, one way or another, analyze frequency response. Also, often enough, you have nonlinear systems, for which Laplace transform doesn't work. Like, it only works so nicely for linear systems. So I understand, like in real life, you would have plenty of situations where you couldn't use these nice tools. But for mechatronical systems, like of small combinations of mechanics and electronics, which we call mechatronic modules, usually drivers, or usually, sorry, motors. Motor is a very typical situation here. You can analyze them using these tools. They're usually linear. If they are not linear, you can sometimes find the linear component in them and do at least some analysis. Okay, you should feel comfortable with it. It's yeah. If you had the classical education in control theory, like 3 semesters, it would be a second nature to you. So I wouldn't have to do this propaganda. But since you are coming from a different background, I want to stress that this thing here, we did this exercise just to show you that even if you don't understand Laplace completely, you can still use it and then verify using standard ODEs. Okay, so that's what I think you should do. If you at some point you feel you don't need to verify, don't verify. Okay, sure, no problem. You can use calculations by hand and but the plotters as a verification or something like this, right? But don't give up on frequency analysis because you feel like Laplace is too strange. All right, sorry for this tirade, but I hope you understand my meaning. How much time do we have until the end of the class? I still have 10 slides, so I'm not sure if we have time. Sound, please tell me.
We have 6 minutes.
6. Okay. So what we're going to do is this. I will finish RL circuit. And then next class, I will talk about RC and RCL. Okay. This was a big lecture, but next lectures are smaller, so we will gain. No problem. Okay, let's go ahead. So now that we did all this analysis for gain in terms of amplitude gain, in terms of input voltage and current, so how current reacts to the input voltage, we could do the same for voltage measured across the resistor. As you remember, we found its transfer function. It is R divided by this thing. And so that will be R times omega I. So R is just a constant factor. So the amplitude gain is going to be just multiplied by this constant factor. So that's it. So you can see it is quite trivial. Transfer function of this guy. So voltage measured across the inductor is, we have a different transfer function here, different transfer function. But the analysis is not very difficult. So this transfer function, first we multiply it again by this guy, but with a minus sign. Again, I think I lost a minus sign here. We would get squares here. And here what we will get is those two expressions. Okay. Where did they come from? It is this guy multiplied by this guy. That's how we get this. Okay. Then we have this guy multiplied by this guy. That's how we get this. Okay, that's what we have. Now, next step, as before, we're going to find absolute value, which means those two things are going to be squared. The denominator is going to pass through unchanged because there's a constant factor, right? We can square it, square root, like take it out of square root, it will remain the same because it is positive. Okay, so we have squares here, which is those same things squared. Now we can take L squared omega squared out of the brackets because it exists quite predictably in both components of the sum. So we take it out of the brackets, and the remaining fraction has a square root of the same expression as in the denominator. So we have this factor that we took out divided by same as before, L squared omega squared plus R squared. So you can see the steps are the same. It's just that here we have to extract a common component here. We wouldn't even have to do it if we just left it out, if we didn't multiply it. If I left it out, it would have been the same. Yes, maybe I should. Maybe I should. Yeah. I don't know. Yeah. So you can see it is it's quite simple. It's quite simple. Thus, we found frequency responses, right? And we we can analyze them in exact same way. We already did it, so I'm not going to repeat. But you can see it is quite um, easy to discuss those things and find those frequency responses. All right, so I will stop here. For the next lecture, we will go over RC circuit and see what kind of filter we get there, and the RCL circuit as well. And after that, we will have a lecture on mechanics. It'll be a quick refresher. It's going to be easy. And after that, we are going to have our lecture on motors. So we are going towards there. If you found that Laplace, like the way I introduced Laplace suddenly was a little bit too much, please refresh it because I'm going to use it for the rest of the semester. Okay. Same about the solutions of differential equations. I'm also going to use it until the end of the semester. So please refresh. If you have some questions or want to ask me for literature recommendations, I'll be happy to provide you. Also, I have specific lecture notes on those topics. So again, I can share my lecture notes, or there are much better lecture notes, obviously, on the internet. So I can recommend some, or you can search for them by yourselves. Just don't ignore the problem if you feel shaky about any of those topics, ODEs or basic stuff about ODEs or Laplace. Right, that is it from me. Do you have any questions? Right, if no questions, then I'll stop the recording.